the fourth. So
this is the fourth. So
hopefully you're not getting bored of listening to me. Unfortunately, my team couldn't come, so I'm the representative of Oak Ridge National Lab. So yes, again, Mengjia couldn't make it. Very sad about it, but I'm gonna talk about her work on this part. I think this talks wraps very nicely the plenary talk that you listened in the morning from Nolan's work on how you can accelerate the installation of connections on facades for overclad panel retrofits. So in that plenary, I mentioned that you might be thinking, okay, if I use the total station to scan a building and then I move it, and then I come back the next day to install the components, how do I know where things are if I move things around? Well, this paper answers that question. And the cool thing is that it uses only one robotic total station, so you don't need to have multiple laser trackers to do this. So all of these, of course, I have to acknowledge Department of Energy for funding of all of these papers. And yeah, Department of Energy and Oak Ridge National Lab are very much interested in facilitating and automating prefabricated construction. We see a lot of potential on this. We see a lot of time savings and automation. And one of the major things of prefabricated construction is that the components can be produced in a very controlled environment and then can be transported to sites where they can be assembled. And the assemble and installation part is the one that we're concerned about on how to automate and accelerate. So because you are not really building walls, but just assembling, you can have a shorter construction time at the job site. You can have higher quality because you can have a better air tightness, given that you can have manufacturing precision. And also there could be less on-site disruption because in this case, we're focusing on overclad panel retrofits. So you don't have to break walls. You don't have to demolish buildings. You just have the building standing and you add basically an extra layer of insulation to make it more efficient. However, the challenges for this to work is that you have to be accurate. Otherwise, if you miss some component, then you're going to have some cumulative error at the end, and then you have to rework or you have to fill some gaps, and that is not fun to do at the job site. So the problems that this paper solves is twofold. First is where is the building? So as I mentioned, you go for the first time, you scan your building in order to get the as-built dimensions and design your panels and design your connections. And then you take your total station away, and then you come back one day later or 1 week or whenever you come back. And then how do you know? First of all, you cannot put the total station in the same place. There is just zero. It is a probability of 0. So you're going to have to put it somewhere else. And how do you know that things are still going to match? So you have to align the physical building with the digital twin, recognizing that you scan the building at an original location, but now you're trying to do the assembly process at the new location. So that's the first problem. And then the second problem is you're installing your panels, and you need to, and you know where your panels are. So each panel has these prisms, 1 prism for tracking, 3 prisms to calculate the orientation. We're treating panels as if they were planes. So you need 3 planes, 3 points on a plane in order to identify where the plane is in space. But then you need to know, okay, if I am in this position and I want to install the panel in a goal position, what is the transformation that I need to do? Turns out that these 2 problems have a very fundamental, very similar mathematics behind it. So that's why they are combined here. So in the first algorithm, we call it resection. That is the usual lingo used in total station language. Basically, what you do is you have to have control points on the building. So whenever you scan your building in the first time, you have these control points that will allow you to align the planes in the future. So then you scan your building, you generate your digital twin with respect to this origin. So the origin of coordinates is here. And then you come back the next day or the next week or whenever you want to do your installation. You put your total station in a new origin. The origin always follows the total station. So now this algorithm on the right describes the steps that you can do in order to move this coordinate system from here to here and align it. So you need to align the orientation of the two coordinate systems. And locally, this is done just by resetting the orientation of the total station. We work under the assumption that you can always level your machine. So the machine is level. You just rotate the orientation in order to make these two coordinates align. And then you have to calculate a translation in order to translate this origin to this origin here. So that is with this algorithm described, so you can see all the details in the paper on how to do it. The second is the transformation, which is also very similar, but it uses a different frame of reference. Here, the goalposts, the frame of reference is with respect to the building where you're going to install the panel. And this reference frame is the panel frame, which is moving. So you're operating this panel, and this reference frame is always moving, is never static. So that is the difference between these two, because the moment that you set your total station down, your frame of reference becomes static. This frame of reference of the panel is more dynamic because you're moving it in space as you're installing it. So a very popular algorithm is called CAPS, which is trying to do the best job at aligning these two coordinate systems at every point in time. So this can work in real time, and in real time gives you the level of rotation that you need to achieve and the level of translation. For our purposes, translation is easy to communicate to construction workers. You can say, move the panel 1 inch to the left, 2 inches up, but giving rotation commands are very tough. You cannot tell somebody, rotate the panel 5 degrees with respect to the z-axis, because what does that mean? So that is something that we're still working on, and this depends a lot on how you are connecting your panels to the building. If you have multiple connection points, then you might be able to shim those connection points in order to incur some rotation, but then you need to know which one and how much to shim, and it's not an easy command to give to an installation crew. Now, if you have a robot, it's easier because the robot understands math, but the construction crew is going to struggle. So this is the lab scale demonstration that we had. Again, this is a 1/3 scale prototype of a 3-story building. We have tape reflectors all over the corners of it. As you can see, they do not have to be aligned. You can just put them wherever. The algorithm takes care of that. They don't have to be at 90 degrees. That doesn't matter. So you just put 4 control points around it. And then what we did is we set up the total station at point A. We shoot the laser. We measure this point B. Then we move total station from point A to point A to point B, and run the resection algorithm, and then measure the quality of it. So in the lab scale demonstration, test number 1 is the baseline error. So this is without moving the total station. So this is just machine error, which is less than 1 millimeter. Once you move the machine, then you incur in some error as big as 4 millimeters. So there is a disclaimer here. The moment that we published this paper, we have been chasing this error for months, but we finally figured out why this error was happening. And the issue is that if you are using tape reflectors and you're asking your total station to look for a tape reflector, the machine might not find the center. It tries to approximate the center, but it doesn't really find the center, and that is the error of the center. But if you manually aim to the tape reflector, then we were able to reduce this error a little bit more. I kept laughing. Okay. So we had this error with the tape reflector, but we were able to reduce it after we chased it because this was driving us crazy. Now the transformation is a little bit different and more accurate because the transformation uses prisms. So prisms are just very, very accurate. So in the transformation, we use prisms to measure the orientation. And then the second way of measuring orientation was this digital protractor to actually measure the angle of rotation. And these are the results. So you can see very low error, less than half a degree for different rotations of the piece. So because we were using prisms to measure orientation, we didn't have the issue that we have with the tapes. So in conclusion, we basically use rotations and translations in order to first solve the problem of finding the building once the digital twin has been created and the trolley station has been moved, and how you can generate transformation commands from one post to another as the panels are being installed. Yeah, and as I mentioned, this paper claims an error of 3 millimeters, but after correction of the error on the tape, we were able to bring this down to 1 millimeter. The angle error was less than half a degree, so we were happy with it. And then what we want to do is basically take this and integrate it with the entire installation process that I described before. So with that, I'll close it for questions or for the next presenter. Thanks.